Exclamation, everybody, and welcome to DLS. It is by Making Art Studios, and it's currently in alpha right now for $5.99. Well, €5.99, I should say. It's out on itch.io. Like I said, early alpha right now, and it's a digital logic simulator, basically a sandbox, which I assume has some puzzle aspects to it. There is a sandbox thing where you can just kind of do whatever you want, but I think when I hit start here, it will go into like a puzzle-like game where you're given a task and you have to try to build the logic circuit necessary to accomplish said tasks. So, like I said, very early here, it's 0.15 right now, so there are some bugs that they say. The sandbox is not quite up to speed yet, all those things, but I figured I'd just take a look at the main game if we can. So, let's do the tutorial just for the sake of argument. I haven't played any of the game yet. So, what we got? Wiring, inverter, wire splitters, components. Okay, wiring. Learn how to create and delete wires. Okay. Play that. In this section, you'll find information about the current level, blah, blah, blah. Press the next page button to start the tutorial. On the left is the schematic view, and on the right is the level view. You create the circuit in the schematic view and see the results of the level view. Press the play button at the top. Press it now to observe the results. Okay. Okay, got it. So then, as was expected, it failed. The LED did not turn on. To start creating a wire, left-click on the switch's output pin. Place as many points on the grid as you want by left-clicking and finish it. You can do that. Okay, finally. In order to delete an existing wire, right-click on it and select Delete from the context menu. Okay, so just go bang like that, and then we hit play. And that should be good. All right. Nice. Move on to the next one. As you learn how to create wires, it's time to meet the first logic gate. At the left of the schematic view, there's a new toolbar with only one button. This is the NOT or inverter gate. This is the NOT or inverter gate. Okay. I think we're putting too many logic words in the sentence here. You can hover your mouse over the button to see some info about the gate. Right, this is just a NOT gate. The NOT or inverter gate, which is what they're saying is it's inverting the signal. It's your NOT gate, but really you're gonna have to fix the English on that because someone's gonna look at that and go, "Not or? What do you mean not or?" Because or is another logic gate. But anyway, I'm guessing they're just gonna want me to drag this down here and go kabang, 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 right? There we go. All right. I'm in the hang of it. There are more types of inputs and outputs in DLS than switches and LEDs. In this case, input A is a 2-bit numeric input, and outputs X and Y are 1-bit numeric outputs. All right. Take a look at the table above. Input A being a 2-bit input can take values from 0 to 3 inclusive, or from 0 to 1, 1 in binary if you prefer. In general, an n-bit number could take 2 to the n minus 1 different values. Yep, anyone who's taken basic computer science courses know that. On the other hand, outputs X and Y are both 1-bit wide, so their values can only be 0 or 1. Careful observation to the table above reveals that X is equal to the most significant bit of A and Y, and Y is equal to the least significant bit. In order to get the individual bits out of A, you have to use a wire splitter. At the left of the schematic view, there's a new button. This is the wire splitter. Right-clicking on it opens its configuration dialog. From there, you can select the number of bits of the splitter. Pressing create will create a new instance. Left-clicking on the toolbar button will create a new splitter using the last used configuration. If you haven't used any yet, the default configuration is a 2-bit wire splitter. Okay. So, 2-bit wire splitter. Okay, create. Put that here, and then connect this. So then what is the, so 0 and 1, which one is the high bit and which one's the low bit? Left click on the toolbar button to create a new instance. Place it anywhere on the grid. Yeah, what's the low bit and what's the high bit? Right clicking on it opens a configuration dialog. You can select the number of bits. We'll create a new splitter. Okay, I guess this is the high and this is the low. Doesn't seem like that should be correct, but alright, let's see. No, obviously I have it reversed. So this has got to be, yeah, this has got to be the high bit, right? And this has got to be a low bit, so this is low. And this is high. Let's see what that does. Yeah, that's, I was going to say, 1 is usually denotes high, right? The opposite of wire splitter is a wire merger. Sometimes you might need to combine multiple 1-bit signals into a wire signal in order to reduce the amount of I/O pins or perform computations in parallel. In this case, the table above is the reverse of the previous level. You have two 1-bit inputs, X and Y, and one 2-bit output A. You'll need a wire merger to merge X and Y into a 2-bit signal and connect it. You can create a wire merger using a new button. And create a new 2-bit wire merger and make the wire connections. Whenever you are ready, press play to connect to test your circuit. Okay. So we'll put this down there. And then I think this was the X was the high X was the high bit and Y is the low bit, I believe. So that should be correct, right? Yep, there it is. Very good. Meet the AND and OR gates. At the left of the schematic view, there are two new buttons. The first one is AND gate, the other is the OR gate. Hover the mouse over them to learn more about how they work. Then take a look at the table above and try to make a connection between the two. Remember that on is equivalent to true, 1 and high. Off is the same as false, 0, or low. If you need some help, move on to the next page. Okay. All right, so left and right. So the inputs are off, and outputs are to both are off, and either is off. Okay, so you say. So that's really just an AND at that point, right? The top one. This one here. So left and right are off, then both and either are off. I see what it's doing. Okay, both and either. All right, so both is AND, either is OR. They're just lining it up that way. So put it this way like this, and I'll move that one back up here. Okay, so then it's just a matter of connecting all these guys up to where they're going to be. Like so. Oh, that's not. I don't want that one. I want this one here. Who's going to put itself in there? That wasn't going to work too well. There we go, and play. Excellent. All right, meet the two universal gates, NAND and NOR. NAND and NOR are called universal gates because they can be used to build every other basic logic gate. There's a section later in the game where you'll have to build circuits with only these two, but let's not get ahead of ourselves. Hover your mouse over to two new buttons and blah, blah, blah. Okay. So none and not both here. So NAND is not both, right? And NOR is none. So we'll just do that, and that, and that, and then we'll connect these two up. Usually that's what it means. So we'll see if I'm correct in my assessment here. Indeed, there we go. Another new gate. This is the exclusive OR gate. Exclusive OR can tell you if one or only one of its inputs is true at a time. In contrast to the OR gate, exclusive OR is false, low, off when both inputs are true. Yep. So put this here. I want only one. This is the what I like to call the Highlander gate. There can be only one. And just connect that up. There we go. All right, sometimes you might need a basic logic gate with multiple inputs. A three-input AND gate works in the same way as a normal two-input AND gate. The output is high if all, yeah, blah, blah, blah. Okay, so sometimes you need multiple inputs, they say. Sometimes you'll need multiple inputs. So 0, 1, 2, 3, 4, 5, 6, 7. Outputs is 1 and all zeros. 3 input gates. So it's 3. Okay, that's the 3 there. That's 3 wide. So wire splitter. And we want the NOR. So truth table above has one 3-bit input and one 1-bit output. 0 is high only when A is equal to 0. In all other cases, 0 is low, meaning that A isn't equal to 0. There are multiple ways to build a circuit for this truth table. You can give it a try right now based on what you've learned so far. When ready, move on to the next page. Okay, so 3-bit inputs. So when A, 3-bit input A and one 1-bit output. 0 is high only when A is equal to 0. So, and that's a 3-bit wide thing. So basically, let's see. So we got NOR, which we don't want. We've got regular OR, and we got NOT. And we got a wire splitter. So I'm probably definitely going to need the wire splitter, I would imagine. Split this out into one gate at a time. Because I don't think these... Or I guess I could make the number of bits 3, right? For these gate configurations. So... I wonder how that works, though. If all of its inputs are low... Well, yeah, I'd still have to use the wire splitter, though. But let's see. So NOR is the gate is logic gate, which produces a high output only if all of its inputs are low, which is exactly what I want. So pull this guy out over here. All right. And then actually I want him to be, he's got to be 3 bits wide. Or I'm sorry, he needs to be, have 3 inputs. Go. Like that. And then I need a wire splitter here. Which actually I need a 3-bit wide wire splitter. There we go. Alright, I connect this guy up here. And then just connect all these across. And this should hopefully do it. Yep, there it is. Alright. Now what do we got? Using splitters and mergers in order to work with a 1-bit signal might be easier to understand, but sometimes it's more natural to treat multi-bit signals in parallel. To do that, you need to create gates with wider inputs and outputs. You've probably already noticed from the previous level that the gate configuration dialog has additional value we didn't touch, the number of bits. This circuit has 2 inputs and 1 output, all 2 bits wide. From the available gates, you can easily deduce that Y should be equal to AND A, B. Take a moment to find out why that's true by looking at the table above. In order to solve the level, you can either use wire splitters and mergers or use a 2-bit AND gate. To do that, right-click on the AND gate. Yeah, okay. So we'll just grab our AND gate. We'll say make it 2 bits wide and 2 inputs. Yeah, okay. So then we go here like that and just connect these guys up straight away. And then that should work here, right? Yep, there it is. Very nice. Okay. So you might have noticed in the previous levels that the initial value of some inputs and outputs is U instead of a number. U means undefined in DLS, and it has a different meaning depending on where it appears. The first interpretation is that the signal value is unknown and can be either high or low. For example, if you want to calculate AND 1 U, you can substitute U with both 0 and 1 and get the results. In this case, AND 1 0 equals 0 and AND 1 1 equals 1. Since the result is different depending on the assumed value of U, the result is said to be undefined, so AND 1 U equals U. On the other hand, AND 0 U equals 0 because there's no value of U which can give a result other than 0. Okay, yeah, I see what they're going for there. The other interpretation of U is what is called high impedance state, or high Z. In DLS, high Z signals are mainly produced by tri-state buffers. A tri-state buffer is a controlled gate. It has one main input, one control input, and one output. When the control input is high, the output of the gate is equal to the input. When the control output is low, the output of the gate is undefined. Tri-state buffers are usually used in conjunction with buses to create additional conditional circuits. A bus is a special component with multiple inputs and one output. The output value is equal to the one and only non-undefined input. If multiple inputs to a bus have a non-undefined value, its output is undefined. With the theory out of the way, let's take a look at the current puzzle. Output Y is low when A and inverse are equal. Otherwise, it's high. This is actually the truth table of the exclusive OR gate, but since we don't have an exclusive OR gate to use, we have to build a circuit using tri-state buffers and buses. If you're ready to give it a try on your own, go ahead. Remember that you can change input values by clicking on them. Otherwise, move on to the next page to read how to build the circuit. Okay. So, let's see. Tri-state buffer. Two inputs, a data input and a control input. Control input acts as a valve. When it's high, the output is the input. When it's low, the output is undefined. Usually used in conjunction with buses to select between several inputs where only one can be active at any moment. Okay. So A and inverse. So A would be 0, 0, 1, 1. Inverse is 0, 1, 0, 1. So we want to put a tri-state buffer here. These are all 1 bit wide. Okay. So put a tri-state buffer here. So we want, so the top is the, let's see if it gives me an explanation of this. The top is the control input. The control input acts as a valve. When it's high, the output is the input. When it's low, the output is undefined. So the output is the input. Output is the input. So then when it's low, it's undefined. When it's low, it's undefined. And not. And what do we have here? A bus. We have a bus. So what does, you think about the bus here again. A bus is a special component with multiple inputs and one output. The output value is equal to the one and only non-undefined input. If multiple inputs to a bus have a non-undefined value, the output is undefined. Okay. So then we have the tri-state buffer. We have a bus. So what I need is, okay, tri-state is the input, the control input, when that's high, the output is the input. So when the control input is high, the output is the input. So if I input a 0 and the control input is high, so then When it's low, the output is undefined. When it's low, the output is undefined. So then an undefined output with the bus will only take an input that is not undefined and push it through. So basically, I think the tri-state buffer is to do the outputs, the high outputs. I think it's to push out the high outputs. And the low outputs are to just go through the bus as normal, maybe? No, it can't be, because one of these inputs has got to be undefined in order for it to only take the one. Otherwise, if they're both not undefined, it will throw undefined out, which is not what I want. So let's think here. So I think A should be... the inputs. And I think inverse should be the control. So what does that give me as we're going down here? So inverse at first is low, which means it'll shove undefined out there. Which is fine. And then the next time around it will be high, which means it'll push 0 out, which is not... Okay, I think I need... Yeah, So... do I need the bus at all? Yeah, I do need the bus, because otherwise it'll go out undefined. And I need a 1... So when it's undefined, what's this other gate? Not. So they gave me a not gate as well. So what that would do is... Yeah, I think I see. So whenever inverse is 1, I want the opposite of what this is going to do. So I think it's pull this guy over here, right? And then we'll attach these two guys. And then this guy will go up here as one of the inputs to the bus. And then the other input would be what? So like that takes care of, like this setup here takes care of this line and this line. So then the other two lines are 0 and 1. How do I deal with them? Because they're just the value of A. So all I have to do is connect A to here, right? Is that true? Because when this is low, it puts out undefined, which should make this undefined. Let's see. I have a feeling this might not be correct here. Let's see. Yeah, it's not correct for... So it was correct for those two, the first and the third. So it's actually the opposite of what I was thinking. The first and third are correct. The second and fourth are not. So when that is 1, so that's when INV is 1, then it's going to transmit the 0, which I'm trying to not But I think what's going on is that A is still going through. And so the bus is not clearing those out. So what it is I need the bus in a different spot here, I think, is what it comes down to. So let's oh, no, I didn't want to clone that. Let's delete that. Let's delete these things right now. Because I think what I need is I think I need the bus. The bus is not first, but it's right after the one thing. So it's going to be tri-state buffer, I think. I think A is going to be the input and inverse is going to be control. So on line 1 here, it's going to be undefined. Right? So I need a 0 to go out to Y. So if I put the bus here, this connects to the bus, so it's going to be undefined, and he has 0 to go out, which would be A, except how would I? The problem is that I need it to be. I need one of these to be undefined if I want the bus to be a thing. Which the bus might be a red herring. It might not be something I need to use. Although I kind of feel like it would be something to use. Because of how this outputs things. Because that would output the correct thing, but then the bus is multiple inputs to the bus have a non-undefined value. The output is undefined. Which I think is what's happening here is I'm getting undefined outputs. Because both of them are not undefined. So I'm wondering if I need 2 of these tri-state gates that are reversed, like one where A is the input and one where inverse is the input. That actually might be something. If I clone this guy, I put him here, and I put A as the control and inverse as the inputs, then that should only give me one and only one defined output. Right? Question is, do I need the not at some point? Let's just see what happens here. Okay, they're all wrong. It's what happens there. I think I need to put the not after each one of these before they get to the bus. So let's delete that. And let's put a not here. And we'll clone that, put one here. I think it works for both. And then the bus, we'll put where we had it. And then connect all these guys. Whoop, connect all these guys. Oh, stop that. Connect all these guys back up. All right, the 2 on the middle are correct, but the first and the last are not. So what am I doing wrong with the first and last? The first one, I wonder if I can I step through the outputs? Do they have like a stepper here? Like where I can just step forward? Because that would be fantastic. That's not what I wanted. Like I'm hoping that they let me step one step at a time here. Can I? Yeah, it's not giving me an option to just step forward one step, because that would be very useful in debugging this. So let's think here. Let's delete this for a second. And let me just look at what this does. Okay, that gets those correct. 0 and the second and the fourth are correct with that one. The first one. So then the ones that's not correct on are where the inverse is low, which makes it undefined, right? So which makes sense because we need something to send through the other side here. But whenever it's, see, it's like 0 and then 1 when it's undefined. So then so that's why it wasn't working, because the A is 0 in that point. So it was making it undefined. And A was 1. So I need... So if I hook A directly up to the thing, that will get us... That will get us the correct stuff? Question mark? No, because it's gonna make it so that it's always... The problem is that it's always going to be defined, so it's going to make it undefined in the areas where it's now correct. So if I put... think here. I admit to being a bit stumped right now. If I put... What if I got rid of that bus altogether? I mean, it still would have the wrong values, right? Let me theorize here for a second. If I delete this bus altogether, and I just connect this straight up here, what do we get? We get the opposite of what I had before. Okay. Which sounds fine. So then that gives me the opposite, which then means if I sent the other signal through, it would be fine? Question mark? No, both of those are when it's undefined, that it's not working. It's undefined, it's not working, so it's got to be... It's got to be just take the value of A when you're undefined. That's definitely where that bus comes in, but it's when the other one is defined, though, it's gonna give me problems. So if I put A, because I have the case of A being 0, that's what's throwing me off, is the very first line there is going to throw me off. because really it should be just take A there. So when I put a bus in here, in the center of all this nonsense, do this, and then we put A there. Connect these up. Yeah, I have the opposite problem. Is that because of the... No, it's not because of the NOT gate. The NOT gate is correct for that. It's because two things have a value. So what does the... What does the NOT gate do if you don't have a... I mean, it's always going to have a value coming through. Because A's always got a value. I mean, I could... Even if I change it so that I use the inverse and just had that... be a not... It's not gonna... Huh. Okay, I'm a little bit stumped as to how this is supposed to go through here. Let's look and see what they say on it. So you have me put a bus down. Right, put the bus near the Y output, yeah. Create the two cases. If inverse is 0, then Y equals A. If inverse is 1, then Y equals not A. Okay. Create a tri-state buffer and place it on the grid. Connect A to its main input. Connect not... Oh, connect not inverse to its control. Oh, I see what they're doing. So... I almost have it here. It's just not quite right. So if I... Let's get rid of some of these, since the lines are all over the place now. Get rid of that. So basically I was on the right track. It's just I need to put the tri-state buffer here. And then I need to put a not here. Right? And then we have this to that, to that, to that, and have that go there. And then the second case, you not A to the main input and connect the other thing directly. So it would be, I would clone this one. See, I had the knots correct. I just had them in the wrong spot. Clone this one. Then this one goes here. This one goes to A. And then up here, and then that should work now, right? Yeah, okay. So I had everything in the that was supposed to be there. I just had them in the wrong spots. I had the knot in the wrong spot. That's what it comes down to. Oh, what do we got? Integrated circuit. Okay, most of the times the circuits you're going to build will be more complex than those presented so far. To keep your schematics as clean as possible, you need a way to encapsulate parts of the circuit into reusable components. You can categorize components into packages. All your packages can be accessed through the component library. And then what? You can start creating a new component by clicking the new component button from the main toolbar. The component editor is the same as the editor in sandbox mode. All options are available when building components. You can also load any schematic you've built in sandbox mode. For more info, blah, blah, blah. While inside the component editor, you still have access to the level view, but you cannot test the circuits. Once you create your component circuit, click on the Componentize Schematic button and select the package you want to add it to, give it a name, and click OK. In order to use your new component, you have to return the level schematic and create a new instance from the component library. Take a look at the truth table and try to create a component for it. Then translate the new component and connect it to the I/O ports. Okay. So we got inputs A and B, X and Y, and then Z. X, Y, and Z. Okay. So inputs A and B. So that could be an AND would be the X, an OR would be the Y, and a NOT would be the Z, right? Because this would be AND would be 0, OR would be that, NOT would be, or exclusive OR, I should say, probably. And yeah, so it looks like it's AND, or, no, I'm sorry, and Y is, no, Y is exclusive OR. So this is AND, exclusive OR, and not maybe? No, not possibly. Or NAT? We'll have to see. I'll have to look a little bit closer. Package default symbol. Okay. So then new components. Oh, I see. Okay. Read-only memory. Oh man, there's a lot of stuff here. A custom component with Lua code. Oh, interesting. LED matrix. Okay, so here's our gates. Got buffer. Got NOR, negative OR. This is high. Only if all its inputs are low. We got NAND. Exclusive OR. One of them was. And either OR and a NOT. Okay. So then if I do the, let's do the exclusive OR one, I think. That in here. And we'll just do inputs would be, I guess I just numeric inputs. All right, that one, and that one, and I guess there's just two inputs, right? A and B, yeah, okay. And then we'll just connect these up to this guy, and then we'll put an output over here, and there we go. All right, and then where do I say componentize this? There it is, componentize schematic. This is exclusive OR, and okay. There we go. So then where's the level schematic at? So go here, exclusive OR, create. So then what we got? We got A and B here. So exclusive OR is the is the Y, I believe. Yes. Yeah, exclusive OR is the Y. So we'll put this guy in front of Y. And then we'll have this connected. And we'll connect these guys up. Whoops, that's what I want. Connect these guys up. Like so. All right, so Y is done. X is AND. So we'll go and new component. We'll do an AND gate right here. We'll do the output on the other side. Two inputs. That one and this one. There we go. Like so. And we componentize that. Make it an AND. There we go. And Turn to the level. And we put the and on the X here. And hook everything up properly. All right, and then Z. Z looks to be what is Z? It looks like it's almost like the opposite of exclusive OR. In fact, it is exactly the opposite of exclusive OR. So I could just do the exclusive OR and then do a not on it. I think that seems like the easiest way to deal with that. So let's just go here, exclusive OR, create that right here, and then it won't let me do anything other than that, huh? So I have to do I have to do a different schematic then. All right, that's fine. Can I use schematics inside of one? It looks like I can. So exclusive OR, create right there. Then we'll put some inputs here into this guy. And then I'll grab a nut 8 somewhere here. Oh, actually, it's doing a NOR, isn't it? No, it's not. No, it's definitely not. I'm looking at the truth table there. I'm like, wait, no, that's not right. Where's my knot at? Here it is, right there. Then we'll get an output. Bang. Connect all the dots. And save this as NXR. I think it's NXOR, but whatever. It is what it is. All right, create that. And come in here. Nope, that's not what I want. I want to come in here. I want to go library, do this, create right there. Hook everything up to it. And this should work, hopefully. Or, you know, it won't work. I kind of wish it would give us some more debugging. Like debugging things here so I can see, so I can step through and see what each of the outputs was. Because if it's showing up on screen here, it's not easily determined. Let me see. Exclusive OR. You see, it's going so fast I can't tell what's happening here. Well, on the last one, we could see that the 1 is wrong for Z. X is correct. Y is correct. So it's definitely this guy here who's giving me the raspberries. Why is that? It's 1 and 1. That should be 0. Oh, because I did, yeah, okay. This is 1, this is 1. Oh, you know what? This is just straight exclusive OR, isn't it? Wait, no. No, it's not. It's not on these, but not on this one. So all these are correct. It's just this one is the outlier, this last thing. Although if that were true, then these would be, yeah, because I put the not on them, I made those reversed, which is not correct. It's actually 1110 are the outputs, or what we're supposed to have as outputs. Somehow I read that differently. So can I edit? No, I guess all I can do is delete it. Okay. Let's delete that. Let's go in here and let's figure out what we're what they really want here. It looks like, so it's got to be like a NAND or something, right? So that's OR. So NOR is not what we want. NAND, that's what it is. We want NAND. Got it. Should have figured as much, I suppose. All right. Not often that I end up using the inverse logic gates, but they are very, very useful. All right, so we'll save that as an AND, an A and V. Do that and turn to level schematic. Grab this guy, create them here, and that should have it. Hopefully. And play. There we go. That's got it. All right. Pretty good. Pretty good. And then now we're into the actual, that was just the tutorial. Now we're into the actual like puzzles here. For the first team, go to the next page. Y equals NOR AB. Y equals not or AB. Right. NOR AB. So it's just, is that all you want? All they gave me was a NAND. So how would I okay. Y is so NAND. That's NAND to NOR. Truth table, what? So if that's, is this not the way? So 0001, I see. I see what they're doing here, kind of. So if I were to do, how would that work? So A NAND B would be 1 for 0 there. But it looks like, so 0 and 1 would be 1, but if I did B there, it would be 1 and 1, would give me 0. And then 1 and 0 gives me 1. But, ooh, so that doesn't quite work. I was trying to see if I could link up B directly to another NAND. Maybe if I linked A to another NAND, but we'd still have the same problem, right? With the 1s and the 0s, it would be, A would be 0, 0 and 1 would be 1. That would still result in a 1 as the output if I did that. So not or A and B with a NAND gate. The low output only if all of its inputs are high. Which works for the last row there, but not for any of the other rows. And all I have is a NAND to work with, it looks like. So I feel like I gotta chain some NANDs together in order to get the output that I'm looking for. But how would I do that? Well, if I NAND a NAND, right, it would be produces a low output if only if its outputs are high. So, yeah, that would only produce zeros then, right? It would be 0. Wait, 0 and 0 would be a 1, which is what I want for the first output, but then everything else, you see, it would just produce 0 for everything except for the last case. So I don't want that per se. That's the only gate they're giving me, huh? That's the only gate they're going to give me is an AND. Because I mean, I could do like the whole, let's just connect these two together, and then put another NAND gate here, and then connect this one to this one, and this one to this one. But I don't think that's going to work. At least not for all cases here. In fact, I'm pretty sure that's not going to work for all cases. Let's just see. Yeah, those last two cases are what it doesn't work. It works for the first two, but not for the last two. I wonder. Oh, I'm wondering. So, if I put a third one there, what would that do? I'm just curious now. I'm not even really doing the math in my head at this point. I'm just like, let me just throw something at the wall here and see what happens. Do that. What is that? What does that produce? Total nonsense. It works for one line, which is kind of what I figured. What I figured was going to happen there. If I put two of these, I'm wondering something here. If I clone this guy and I do the exact same thing on this one, right? And then I put another one out front. What exactly does that do? Besides create a freaking mess. Actually gets 2 out of 4, huh? Because you know it's got to be some kind of combination of this, right? Let's look for hints. Not x equals NAND XX. X equals NAND XX. I think what they're saying here. Maybe I'm like closer to the answer than I think I am. If I do this and this, what does that give me? A whole lot of wrong answers. That's what it gives me. But I delete this guy. I have this go straight in there. Okay, 2 out of 4. 2 out of 4. All right. Or AB is NAND, not A, not B. Right? NAND, not A, not B. Which is what I had before, right? So it'd be interesting to see if it was. So if I clone this guy, I come here, and I say, do this, and do that. Yeah, that's a whole kind of that's just mess. That's just a mess. So x equals NAND A, NAND B, and y equals NAND XX. So what they've got, you knew it had to be a combination of all of these, right? Move this guy up here. So they've got this and this, right? Going into this, right? And then that goes into here. And here. Okay, that's crazy pants. That's crazy pants. Yeah, that worked. I figured it had to be something crazy like that, but geez Louise. Now it's like build an exclusive OR gate using its complement exclusive NOR, using only NAND gates. Yeah, it's going to be. So it looks like the puzzles are going to be like, how many NAND gates can you chain together to get this other thing to work, which is crazy pants. But I guess that makes a lot of sense since when you're dealing with integrated circuits and whatnot, the gates all have a certain complexity to them, and if you can reduce the complexity, you can reduce probably the power output and all that stuff. But holy hell, man, holy hell! I'm going to stop there because my brain is fried. But this, my friends, has been. Let me get back to the menu if I can here. I do wish they had like a debugging thing where I could step through it. But let's go back to the menu. This, my friends, has been DLS. It is by Making Art Studios, and it's currently early alpha. It's 0.15.0. It's currently €5.99 out on itch.io. If you want to go take a look at it, dig into it. Like I said, there's a whole sandbox mode where you can play around with things. There was, as you saw from the components, you can do some Lua scripting if you really want to and make your own components out of it, so you can get full on programming there. But again, it is an alpha version, so there's going to be bugs and simulation problems and whatnot. But so far, so good, I'd say, on this front. So as always, I'll leave links down in the description so you can do your own due diligence. Thanks so much for watching, everybody, and I will see you next time.